So hello everyone. So now we'll start the fourth lecture of vector algebra. Here we'll discuss the Cauchy-Schwarz inequality. Okay, vector algebra. This is lecture 4. Okay. So what we will discuss, this one can refer to as a theorem. This is very important inequality. The Cauchy-Schwarz inequality. Okay. So what does it say? What is the statement? Okay. So it basically connects the dot product and it gives some inequality involving dot product of two vectors. Okay. So let A and B are two vectors in Rn, then A dot B whole square is less than equal to A dot A multiplied with B dot B. Also, the equality holds if and only if A equal to CB for some scalar C. Okay, this C can be 0 or non-zero, we don't know. So we'll prove this. To prove this, what is this inequality that we want to prove? We have A dot B whole square is less than or equal to A dot A plus A multiplied with B dot B. Okay. So of course observe that, let's name it as equation 1 point, inequality 1.1. So 1.1 is true if either A or B is 0 or the null vector, right? Because if A is 0, then the left side will be 0 and right side is always non-negative, right? Because A dot A is bigger than or equal to 0 by definition, B dot B is bigger than or equal to 0 by definition. If B is 0, similar logic will work. Okay. So the proof is fine if one of them is 0. Also, in that case, basically the right side is also 0 if one of them is 0, right? So all the whole statement is true, this inequality and A equal to C of B, because if A is 0, 0 equal to C times B, it takes C equals to 0, right? If B is 0, B equals to 0 times A. Okay. So fine. So let both A and B are non-zero vectors. Okay. So now let this is non-zero vector. Now you consider that basically this thing that x equals to B dot B, which is non-zero, and y equals to A dot B, which we do not know, is some scalar quantity. So then xa minus yb whole square is exactly xa minus yb dot xa minus yb, and A dot A, basically, I mean, this is the dot product of the vector itself, which is always non-negative. Okay. Now you use the product rule, dot product rule, basically the distributive property. So multiply this with this and this. So this is basically xa minus yb dot xa, okay, minus xa minus yb dot yb, this is bigger than equal to 0. So this is x square A dot A minus xy B dot A minus xy A dot B plus y square B dot B, which is bigger than equal to 0, and this means that x square a dot a minus 2xy a dot b plus y square b dot b is bigger than or equal to 0. And once you have this, we know what is the value of x and y, right? Yes. So if b is non-zero, so since b is not the zero vector, so by the previous property in the previous lecture, we know that b dot b, which is x, is strictly positive. So you can divide by x. Okay. So dividing both sides of the above inequality with x, we get that x into a dot a minus 2y into a dot b plus y square is bigger than or equal to 0, but a dot b is y, so this is x a dot a minus 2y, this is 2y square b, because y is equal to a dot b. So that means that x into a dot a minus y square is bigger than or equal to 0. That means y square is less than or equal to x into a dot a. And what is y? A dot b whole square. X is b dot b into a dot a. But this is same as a dot a multiplied with b dot b. This is which is 1.1, right? So this is the Cauchy-Schwarz inequality. Now let the equality holds. That means suppose this is a dot a multiplied with b dot b. So if this is same, that means 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 this quantity is equal to 0. So basically if this is equal, then we say that xa minus yb whole square is 0. Okay. Once that is 0, that means we know by the previous property that means the dot product of this vector itself is 0, and this is 0 only when this vector is itself 0. Okay, by the previous property on the previous lecture. Okay, so that then we say that xa minus yb whole square is 0. That says that xa minus yb is the 0 vector. Okay, it's xa equal to yb. Okay, so this completes the proof. This says that x is a scalar multiple, x is a scalar multiple, a is a scalar multiple of the vector b. So a and b are dependent. Okay, in other sense. Okay, yes. So we'll stop here. In the next lecture we will define what is the length of a vector. Also we'll prove another important inequality called the triangle. This is lecture 4.